Okay, students, in last class we have learned about the transport phenomena. అభిగమన దృగ్విషయాలు అంటే ఏంటో చూసాం. So what is transport phenomena? Whenever a gaseous state not in thermal equilibrium, then the following three cases may happen. What are those? Viscosity, thermal conduction and diffusion. So viscosity will be happen due to the transport of momentum from high velocity region to low velocity region. Similarly, thermal conduction may happen that because of the transport of heat energy from high temperature region to low temperature regions. Similarly, diffusion may happen due to the transport of mass from high molecular density region to low molecular density region. So all these three phenomena happening due to the transport of momentum, heat energy and mass respectively. These are called transport phenomena. Transport phenomena. So all these may happen only whenever the system is in non-thermal equilibrium. Non-thermal equilibrium. Now, in today's class, we are going to derive the equations for coefficient of viscosity and coefficient of thermal conductivity, coefficient of thermal conductivity and coefficient of diffusion. Coefficient of diffusion. So now at first we are going to derive equation for coefficient of viscosity. You know what is viscosity? It is a transport phenomena. Will happen whenever the gaseous system not in thermal equilibrium. Due to that, there are some differences in the velocities in different layers. Due to that, momentum may transmute from high velocity layers to low velocity layers. So because of that, viscous force will arise in between these layers. This force opposes the relative motion in between the layers. This viscous force can be explained by the factor coefficient of viscosity, that is eta. So by using this coefficient of viscosity, one can quantitatively estimate the viscous force in between the layers of the system. Okay. So this coefficient of viscosity eta is derived by the Maxwell by using the factor mean free path. So we already learned about mean free path. So this is denoted by lambda. What is mean free path? The average distance traveled by the molecule between two successive collisions. That is called mean free path. Okay. Now, how one can derive coefficient of viscosity eta, which is quantitatively estimates the viscous force in between which opposes the relative motion in between the layers. Okay. So let us see this figure. So as shown in the figure, let the gas is floating, or the gas is moving along the OX axis. Let the gas is moving along the OX axis. So as I said yesterday, every fluid can be considered as a group of so many layers which are parallel to each other. Now here also the gas can have, let us assume that the gas can have so many layers, are considered to be so many layers. These layers are parallel to this OX axis, and they are along the OY axis. They are parallel to the OX axis, and they are along with the OY axis. Okay. Now, as the gas is moving along the OX axis, the layers of the gas which are in contact with the OX axis, let us assume that they are having zero velocity. So OX యాక్సిస్ తోటి కాంటాక్ట్ లో ఉన్నటువంటి లేయర్స్ యొక్క వేగము శూన్యంగా భావిద్దాం. Then from that point onwards, the from OX axis onwards, the velocity of the layers slowly increasing with a velocity gradient along the OY axis. That means the velocity of the layers increasing step by step with a velocity gradient, that is du by dy along OY axis. So now what is the velocity gradient here? Du by dy. So the velocity of the layers increasing with a velocity gradient along the OY axis from OX axis. Okay. Now let us take three layers from OX axis. That is AB layer, CD layer, and EF layer. Now let's assume that the velocity of the AB layer is U. Now let us take another layer CD, which is on the upper side of the AB layer at a distance of mean free path, that is lambda. So AB కి ఎగువ భాగాన మరొక లేయరు AB నుంచి ఎంత దూరంలో తీసుకుంటున్నాము? మీన్ ఫ్రీ పాత్ దూరంలో తీసుకుంటున్నాము. Now let's assume that the velocity of this layer will be u plus lambda du by dv. Why? Because the velocity is increasing from OX axis with a velocity gradient du by dy, and this layer is at a distance of mean free path from the AB layer. That is why lambda into du by dy plus, now what is the velocity of the AB layer? U. Now the next layer above this layer can have the more velocity when compared to the lower layer, that is AB. That is why the velocity of the CD layer will be more when compared to the velocity of the AB layer. So that the velocity of the AB layer can be written as u plus lambda du by dy. Similarly, let us take another layer which is below this layer AB, that is EF. Now this layer is also can be taken at a distance from AB at a distance mean free path distance from the layer AB, so that automatically the velocity of this layer will be less when we compare to the velocity of the layer AB. Now that is why the velocity of this layer can be written as u minus lambda du by dy. So like this, you have taken three layers and you have written the velocity of these three layers. Okay. Now, what will happen? The viscous force which is arised in between these layers is directly proportional to the velocity gradient du by dy. So, because of the differences in between the velocities of because of the differences of the velocities in between these layers, a viscous force will arise. This force opposes the relative motion in between these layers. This high velocity layer try to drag this layer to the uh, drag this layer. At the same time, this slowly moving layer try to drag this layer. That means there is a this viscous force will arise which opposes the relative motion in between these layers. So the fastly moving layer tries to drag this layer with that layer. At the same time, the slowly moving layer tries to drag this layer to the backwards. So like that, a viscous force will arise in between these layers. So this viscous force which has arisen is directly proportional to this value, that is velocity gradient du by dy. So you see, so the viscous force is directly proportional to the velocity gradient du by dy. So if you want to remove this proportionality, you have to multiply this value with some constant. So f is equal to minus eta du by dy. Therefore, eta can be written as minus f by du by dy. This constant eta is called coefficient of viscosity. Why we are using minus negative sign here? Here, negative sign indicates that the viscous force decreases as we are going away from the surface of the contact. So, this viscous force will be decreases as we go away from the surface contact. Why? Because the layers which are in contact with the OX have zero velocity, but the layers from this OX surface onwards, the velocity of the layers will increases with a velocity gradient du by dy. That is why the viscous force decreases as the velocity gradient increases. Okay, now, so this negative sign indicates that value. Or in other words, the negative sign indicates that this viscous force acts in the opposite direction to the velocity gradient. In opposite direction to the velocity. The velocity gradient is along the OY axis, whereas the viscous force along the negative OY axis. Okay, so that is why also we can use the negative sign here. So from these equations, we have written as eta equal to minus f by du by dy. Okay, now we have to find out here the viscous force F, and you have to substitute that in this value, in this equation, then you can get the value of eta, that is coefficient of viscosity, which estimates the viscous force in between the layers. Okay, now how to find out the value of F? So you see, let the number of molecules per unit volume of the gas be n. కనుక మనం తీసుకున్న వాయు వ్యవస్థలో ప్రమాణ ఘనపరిమాణానికి ఉండేటువంటి అణువుల సంఖ్య ఎంత అనుకుంటున్నాము? n. మాస్ ఆఫ్ ద ఈచ్ మాలిక్యూల్ ఈజ్ m. ప్రతి ఒక్క అణువు యొక్క ద్రవ్యరాశి ఎంత అనుకుంటున్నాము? m. నెక్స్ట్, and the average velocity of the gas molecules is c1. సో ప్రతి అణువు యొక్క సరాసరి వేగము ఈ వాయు వ్యవస్థ నందు ఎంత అనుకుంటున్నాము? c1. The number of molecules per unit, let the number of molecules per unit volume is n, and mass of the each molecule is m, and let the average velocity of the each molecule is c1. Then, as per the Joule's assumption, this is very crucial point and important point. As per the Joule's assumption, the number of molecules crossing a layer upwards or downwards, the number of molecules crossing a layer upward direction or downward direction per unit area per second will be nc bar by 6. Will be nc bar by 6. So, according to Joule's assumption, the number of molecules crossing the layer. Let us take this middle layer. So, the number of molecules crossing the layer in downwards direction or upward direction. You see, like this. Per unit area per second will be nc bar by 6. This is what given by, assumed by Joule. So, the number of molecules crossing the layer in the downward direction, in the upward direction, from upper layer to this layer and lower layer to this layer will be nc bar by 6. You should use this equation in the derivation of eta. This is very, very, very important point. Okay. Now, we can write, so what is viscosity? The transport of momentum from higher velocity region to lower velocity region, or from lower velocity region to high velocity region. The transport of momentum like this in downward and upward directions. Okay, now we can write in that manner. The momentum carried downward by the molecules crossing per unit area of AB layer per second. Let this is P1. So the momentum carried downwards from CD layer to AB layer per unit area per second. Let it will be P1. Then what is the equation for momentum? Mass into velocity. Mass into velocity. Now, in the above paragraph, we said that number of molecules per unit area is n, and at the same time, mass of the each molecule is m. Each molecule is m. Now, what is mass here? So, the number of molecules crossing upward and downward direction per unit area per second is nc bar by 6 as per Joule assumption. What is the mass of the each molecule? M. Now, the total mass will be m and c bar by 6. M and c bar by 6. Now, so mass can be written as m and c bar by 6. Now, what is the velocity? So, as we are writing about the momentum in the downward direction from high velocity layer to lower velocity layer, we have to write these molecules can have high velocity. What is the velocity? U plus lambda du by dy. So, first of all, I have written that the momentum carried downward direction from CD to AB layer per unit area per second will be P1 equal to mass into velocity, that means mnc bar by 6 into u plus lambda du by d. Similarly, now I can write the momentum carried upward direction from EF layer to AB layer, per unit area per second will be P2 equal to mass into velocity. Already we have written mass. What is mass? mnc bar by 6 into what is the velocity of the molecules which are in the EF layer? U minus lambda du by d. So that is why I can write u minus lambda du by d. So I have split the transport of momentum in the upward direction, in the downward direction. The transport of momentum from upper layer to lower layer, let us, if you take that as a P1, then P1 can be written as like this. If the transport of momentum from lower velocity layer to higher velocity layer, that is from EF to AB, that can be written as P2. If you write it as a P2, then P2 equal to mnc bar by 6 u minus lambda du by dy. So now what is the net momentum? What is the net momentum transferred per unit area per seconds into the layer AB? What is from upward direction, from downward direction? What is the net momentum here transferred to the layer AB per unit area per second can be written as P equal to P2 minus P1 equal to P2 minus P1. You know what is P2 here? Mn C bar by 6 into U minus lambda du by dy. This is P2. Similarly, you know what is P1 here? Mn C bar by 6 into U plus lambda du by dy. Okay, this is P1. Now, if you subtract this P1 from P2, you can get the net momentum transfer to the layer AB per unit area per second. Okay. Now, if you take this PMNC bar by 6 as common, then within the brackets you have U minus lambda du by dy minus U minus lambda du by dy. Now, this U and minus U will be cancelled out. Then you can get P equal to MNC bar by 6 into minus lambda du by dy minus lambda du by dy here. So, if you add these two values, then you can get minus 2 lambda du by dy. So, here 2 ones are 2 threes. So, you can get P equal to MNC bar by 3 into lambda du by dy. So, this is the net momentum transferred to the layer AB from the upward and from the downward direction per unit area per second will be P equal to MNC bar lambda by 3 into du by dy. So, this change in momentum per second is equal to the viscous force per unit area. So, this is the net. This net momentum can act as a viscous force in between the layers, which opposes the relative motion in between the layers. So, you have to substitute this net momentum as a viscous force in the equation number 1. So, what is equation number 1 here? So, eta equal to minus f by du by dy. So, this is the velocity gradient and this is the viscous force. So, now in place of this viscous force, you have to substitute the net momentum. Why? Because net momentum is itself can act as a viscous force in between the layers. So, if you substitute that one, eta equal to, what is the net momentum here? Minus MNC bar lambda by 3 into du by dy by whole by du by dy. Here we have minus, and already in eta equation you have minus. Minus into minus plus. Okay. Now this du by dy and this du by dy will be cancelled out. And we can get eta as eta equal to MNC bar lambda by 3, that equal to 1 by 3. So, MNC bar lambda by 3. So, here you can substitute. This is where rho equal to. So, here we have m into n. So, this Mn gives us the density of the gas, and n is the number of molecules per unit volume, and m is the mass of each molecule. So, these two together, multiplication of these two gives us the density of the gas. So, instead of this value Mn, we can substitute the value rho. Therefore, eta equal to 1/3 into rho into C bar lambda. What is lambda here? Mean free path. So, what is mean free path? The average distance traveled by the molecule in between the two successive collisions in the gaseous system. Okay. So, the value of this mean free path lambda equal to 1 by root 2 pi sigma square n, whereas sigma is the diameter of the molecule. So, eta equal to, so if you substitute this value in the equation number 5, what will happen here? You see, eta equal to Mn C bar or rho directly we can use this equation. You see, Mn C bar by 3 root 2 pi sigma square n. If you cancel out the n in the numerator and the n in the denominator, then eta equal to mcr by 3 root 2 pi sigma square. So this is the equation for coefficient of viscosity, which explains the viscous force or viscous force in between the layers. Eta equal to mc bar by 3 root 2 pi sigma square. So this is how one can derive the equation for coefficient of viscosity. So it will be derived very easily by using uh, Joule's assumption, in fact, Joule's assumption. So this is explained by Maxwell by using mean free path. So you see, so we can see it once again. So let us take a gas which is moving along the y-axis. The layers which are in contact with the y-axis have zero velocity, and the velocity is constantly increasing with the velocity gradient du by dy to the layer along the OY axis. Then let us take three layers AB, EF, and CD. Let us take the velocity of the layer AB is u. Then if you take a layer CD above the layer AB at a distance lambda, that is mean free path lambda, then the velocity of that layer will be u plus lambda du by dy. Similarly, if you take another layer, that is EF, below the layer AB at a distance of mean free path lambda, then the velocity of that layer will be u minus lambda du by dy. Now, the viscous force which arises in between these layers because of the differences in the velocities of the layers is directly proportional to the velocity gradient du by dy. So, this f is directly proportional to minus du by dy. Okay, this can be written as f equal to some constant minus eta into du by dy, where eta equal to minus f by du by dy. So this theta is called coefficient of viscosity. Here, minus sign indicates that this viscous force acts opposite direction to the velocity of the velocity gradient. Okay, now what is the how one can find out the expression for eta? So you have to find out the viscous force, and then we have to substitute that value in this, then you can get the expression for eta. So for that, we can go for Joule's assumption. What is Joule's assumption? If the number of molecules per unit volume is n, and the mass of the each molecule is m, and the average velocity of the gas molecules is c bar, then as per the Joule's assumption, the number of molecules crossing the layers upwards and downward directions, upward and downward direction per unit area per second, upward and downward direction per unit area per second will be nc bar by 6. By taking this equation, we can easily derive the expression for eta. So now we can write what is the momentum carried downward direction from the layer CD to AB per unit area per second will be P1 equal to mass into velocity, that is mnc bar by 6. So here into what is the velocity u plus lambda du by dy, because the upper layer CD can have the velocity u plus lambda du by dy. Similarly, we can write the amount of momentum carried upward direction to the layer AB from the layer EF per unit area per second will be Pt equal to mnc bar by 6 into u minus lambda du by dy. Now, what is the net momentum transferred in the layer to the layer AB per unit area per second will be P equal to P2 minus P1. So if you substitute P2 value and you have to subtract P1 value from P2, you can get this value. Here, the change in momentum can act as a viscous force in between these two, in between the layers. So you have to take this value as a viscous force, and you have to substitute this in the equation number 1. Then you can get mnc bar by lambda, where mn gives us the density of the gas. If you substitute the value of mean free path lambda, that is m 1 by root 2 pi sigma square, and then eta will be mnc bar by 3 root 2 pi sigma square n. So if you cancel out n and n values, eta will be mc bar by 3 root 2 pi sigma square. Okay, so same like this, we can derive the expression for thermal conductivity also, coefficient of thermal conductivity also. Coefficient of thermal conductivity also. So you have to make a chart, you have to work on this. So in a similar manner, just like coefficient of viscosity, you can easily find out the expression for thermal equation, coefficient of thermal conductivity also.